Start using Smith charts to make unruly loads behave well at RF frequencies. We're also going to discover that we need to have a good handle on second-order RLC circuits to do that. The idea of building circuits to make loads behave better is captured by the schematic I've drawn here. I've added a box between the load impedance and the transmission line, which represents a circuit we will design that's called a matching network. We've seen that adding components in shunts or series changes where a load is represented on a Smith chart, and we're going to use that fact to make loads look like 50 ohms by adding the right shunt and series components. We're calling the impedance looking into a matching network ZM, and we're calling the reflection coefficient looking into a matching network gamma M. We're trying to put a circuit in the matching network box that will set gamma M to 0, or equivalently, set the value of ZM equal to Z0. So let's consider one of the simplest examples of matching networks. Here, our load has some inductance in series with it, maybe from a poorly designed via that connects it to ground. We're going to put our unmatched load on the Smith chart, which, as a reminder, we do by calculating Rn and Xn. So we divide both the resistance and reactance of the load by Z0, and find Rn is equal to 1 and Xn is equal to 1, which we represent on the Rn is equal to 1 circle and Xn equals 1 arc on the Smith chart over here. Note, I'm using some goofy notation in this calculation. Here I'm using G to stand for giga and N to stand for nano, which means G times N is 1. This Zn value is promising. Because Rn is equal to 1, we almost have a good match. We just need to take care of the non-zero Xn with our matching network. Fortunately, capacitors have negative resistance, negative reactance, so we might consider a network that looks like this to cancel out the positive reactance from the inductor. I've picked this value of capacitance strategically, and we can see why by computing the normalized match impedance Zm. It's given by almost the same expression as the normalized load impedance, but we have to add the capacitor's impedance in series, and we find the capacitor reactance exactly cancels the inductor reactance. That means Zm is 50 and gamma M is 0 as desired. We can see that on the Smith chart too. Adding the capacitor has moved the load along the Rn equals 1 circle to the origin of the gamma plane. So, adding the capacitor moved us along this arc. This is great, we achieved our goal. However, you might wonder whether this network will work at any other frequency than the 5 gigaradian per second driving frequency. Answering that question requires us to take a close look at the load we've made, which is a series RLC network. You might recall that series RLC networks are governed by second-order differential equations that often have interesting behavior, including resonance. I mention this because we're relying on resonance in the matching network. If we calculate the resonant frequency of the network, we discover that it's the same as the drive frequency, and that calculation is down here, where P is standing for pico. Because we are relying on resonance in order to cancel the inductive reactance, this technique is often called ringing out, because a resonating system is often referred to as ringing. So we are ringing out the inductive impedance. As a final note, you can ring out shunt components too. You just write an admittance equation instead of an impedance equation to find a very similar set of behaviors. Finally, as a bit of vocabulary, it's common to refer to an RLC circuit as a tank. So in summary, matching networks are circuits we design to make loads look like Z0. You can cancel out series or shunt reactance by adding the other component in series or shunt. So capacitors can cancel out inductors, or inductors can cancel out capacitors. And canceling impedances relies on resonance, which has implications for the bandwidth of our matching network and other performance parameters.